Good evening. Welcome, and thank you for coming out tonight. If anybody is here for the Rosemount Eastview football game, you're in the wrong place. But I think if you stay here, you'll appreciate it. My name is Norm Rickman. I'm on the board of the advisors for the Heller-Hurwicz Economics Institute, our host for the night. And my job is to welcome you again and thank you for coming. With all the other activities going on, we really do appreciate it. You're in for a great discussion on the economic impact of climate change, and I think it's going to be well worth your time. Now, I'm a 71 graduate of U of M economics undergraduate. I'm not a PhD like these folks. But if you think 71, that was about the last time that the Gophers won 4 Big Ten football games in a row. And we can do that Saturday. Okay? Yeah, right. Yeah. And you're probably asking, well, yeah, that's interesting, but what does that have to do with tonight's topic? Well, apparently hell is freezing over. HHEI, Heller-Hurwicz Economic Institute, was founded in 2010, so it's relatively new if you're not familiar with it. Its mission is to inform and influence public policy through leading-edge, unbiased, fact-based economic research. And then, as importantly, to communicate that research to policymakers, business executives, and other academics. It's housed in the College of Liberal Arts Economics Department at the university, and it's named after two, as you probably all know, two Minnesota economics giants, Nobelist Leo Hurwicz and Walter Heller, who served on was chair of the President's Council of Economic Advisors for both Kennedy and Johnson. Their legacy, demonstrated in both their theories and their practices, is that public policy can indeed achieve societal goals, but here's the kicker: it has to be properly designed and properly implemented, and that's the driver for what goes on at HHEI. We have 3 established focus areas for research. One is social insurance, another is reforming financial markets, and the third is climate change, which is our topic for tonight. This is actually the second roundtable we've done on climate change, the first being in 2011. Yeah. One of the speakers at that session is tonight's moderator, who I'll introduce in a minute, Bob Litterman. Bob got his PhD from Minnesota, economics in 1979. Well, it just seemed that long with all your accomplishments. It had to be 100 years. After a successful career on Wall Street, Bob is now semi-retired. Although he finds time to serve on a variety of boards, he's the chairman of the advisory board for Key Post Management. He's also a fellow member with us on the advisory board of HHEI. He writes and speaks frequently on this topic, the economic impact of climate change. So we're in very good hands. Bob will introduce the topic in more detail, and we'll then introduce tonight's panel and take us through the discussion. So again, thank you for coming, and those cheers are for me. Thank you. Bob.
Thank you, Norm. It's a great pleasure to be here. The Heller-Hurwicz Economics Institute, I think, is a wonderful institution to try and take the ideas that have been developed in the economics department here and try and apply them more broadly to some of the important topics facing society. And tonight's topic, climate risk, is certainly one of them. As Norm mentioned, I was trained here, and when you're trained in the economics department at Minnesota, you learn a certain way of thinking. I left academia a long time ago, went to Wall Street, and had a very nice career at Goldman Sachs on the quantitative side. Back in 1994, Goldman asked me to be the head of risk management for the firm. They taught me a lot about risk management. one of the things they taught me is that the role of the risk manager is not to manage risk. The role of the risk manager is to identify risks, to quantify those risks, to think very carefully about worst-case scenarios, and to provide the information that's needed to the folks who run, in the case of Goldman, who ran the firm and therefore made the decisions. And when you think about managing risk, the key is not to minimize risk. The firm was not trying to avoid risk. What the firm was trying to do was to make as much money as possible. And the way to do that, as in all investments, is to understand the risks that you're taking and to make sure that you're getting paid for those risks. So that kind of background in finance and thinking about that led me, after I retired, to start thinking about some of the other risks, and in particular climate risk, and is it being priced appropriately? It certainly didn't seem to me that it was. And as I tried to read the literature about climate risk and understand it, I found, well, two things. One is it's very interesting. It's a very, I think it was viewed as a simpler topic maybe. Didn't attract a lot of attention, although people were working in this area for decades. But more recently, there's been a focus on some of the more interesting and I think difficult issues associated with climate risk, and we have two very excellent economists here tonight to take us through kind of the state of the art in thinking about climate risk. Now, the first Heller-Hurwicz Economics Institute session on climate risk, Richard Sandor and myself both talked about what is the appropriate incentive to avoid creating additional emissions. Clearly, greenhouse gases now are creating an externality. They're creating risk to future generations. The latest IPCC report that was released about 6 weeks ago made very clear that there's very little uncertainty about the reality of climate risk. And actually, the response to that report I thought was very interesting, because there wasn't too much denial going on. There were very few people who said, no, this isn't real. Rather, the folks who have been on the denier side of this political argument focused on the fact that temperatures haven't risen much in the last 10 years. Now, they're clearly higher over the last decade than they were the decade before and the decade before that, but the argument was, well, maybe things aren't as bad as we had thought, and maybe they're not. But the point is, when you start focusing on how bad might things be, you're really arguing about what's the appropriate incentive. That's really a question of, should the price for creating emissions be higher or should it be lower? And that's kind of one of the fundamental questions. But answering that question is very difficult for economists. It's not a simple cost-benefit analysis, in part because the damages are very far into the future, and that raises issues. How do you discount damages that might be 50 or 100 or 200 years from now? And the second reason it's very difficult is because we really have no idea how big those damages might be. This is the first time we're doing this experiment on a very complex system. And so it's very hard to quantify worst-case scenarios. How much should you worry about those worst-case scenarios, and what is the appropriate incentive to conserve on emissions? So that's the basic framing of the issues that we're going to talk about. And let me introduce the two speakers who are going to give presentations. I think we're going to have about 15 minutes for each, followed by a panel discussion and plenty of time for questions from the audience. Our first speaker is Per Krusell. Is that Krusell? Krusell. Professor of economics at Stockholm University. Per got his PhD here at Minnesota in 1992, and then has had a number of positions in the United States before going back to Sweden. He was a professor at Princeton. Before that, had positions at Rochester, University of Pennsylvania, and Northwestern University. And perhaps I'll introduce Steve Polasky as well. Right now, Steve is a professor here in the He's the Fessler-Lampert Professor of Ecological and Environmental Economics and is an interdisciplinary chair in the Department of Applied Economics and Ecology, Evolution, and Behavior here at the University of Minnesota, and came to Minnesota after having previous positions at Boston College and Oregon State University. So with that, let me turn it over to Per, and then we'll follow with Steve.
All right. Thanks a lot for inviting me to this interesting discussion. It's great to be back in Minnesota. And I'm going to do a little bit of the cost-benefit analysis that you were just mentioning here, Bob. And as you can see from the title, it's going to be macroeconomic cost-benefit analysis of carbon dioxide emissions. And my background here is really not one of being an expert in climate science. Of course, I'm an economist. And as of maybe 5 years ago, I pretty much didn't know anything about the area, but was asked to participate as a macroeconomist in this research project that spanned over disciplines in Stockholm. And I've been collaborating with people there, but also with people in the US on this. So it's really like a broad research network. Why did they ask me? I think the questions are really macro questions. They're global questions, so macroeconomists are good for this. I think I have had and have the right tools, and I'm pointing out here that this is not just like being nice to Minnesota. I really think it's true that we really received, back in those days at least, I don't know now, I don't know. But I mean, it was just this supreme education in macro. So in a way, I'm really happy to come back and say thanks for that toolkit. And I should also mention that I'm kind of a boring person in this area because I'm not coming into it as a convinced person on one side or the other. I mean, I had really no prior and had to basically figure out by talking mainly to natural scientists in the beginning, but then thinking about the questions from the economics perspective, macro perspective, what we had to think about, and then put in numbers and do the boring economist cost-benefit analysis that I think is crucial, and maybe we'll discuss this more, whether it makes sense to do it and do it this way. But so today I'll basically talk about the main arguments in that calculation, which is not super exciting perhaps, but I think the area is so important that you have to do it. So I'm going to force you through some boring stuff here. And the boring stuff involves what we call integrated assessment models. And the integration is to integrate economics and climate science, essentially, and the feedbacks between them. And I would like to say that I think that the integrated assessment models that I have worked on and worked with combine state-of-the-art stuff from these three areas. I mean, global macroeconomics, climate modeling, and carbon cycle modeling. And I should also say that the calculations I'll be presenting, they mainly derive from the first aggregation here I'm talking about. When you think about the world as a whole, just as one region, it's easy to do the cost-benefit calculation thinking of the world as just having one region, but actually it's super important for some perspectives to disaggregate the model and have many regions and to see how different regions are affected differently. I'll just say one word on that today, but it will mainly be thinking of the world as a whole. And I'll start by just stating briefly the broad conclusions, and then I'll go through the arguments one by one. So can you see this? Yes, you can. One conclusion, I mean, and this is not just my conclusion, but it is also the conclusion we come up with, is that climate change is associated with significant global damages. They are very unevenly distributed across the world. I mean, the biggest damages we estimate will tend to happen in poor parts of the world. And I also have to say that our reading of the literature is that the costs are likely not catastrophically large. So that likely means the absolutely most likely thing is that we will not have catastrophe, but we'll discuss the issue later as to whether there might be some chance of really, really large numbers. I'll be going through a calculation that's hard to show today, but I think we have a robust result in this publication that I'm mentioning here on how to compute and what the number is, the optimal policy. And the optimal policy is to tax CO2 at a relatively modest level, I would argue. Modest in the sense that it's not a scary tax, it's not a tax that will stop our economies from functioning. So we compute the thing to do. And I should also mention that the analysis that I'll be going through actually incorporates uncertainty risks. So it's not like it doesn't incorporate that, and we can discuss later whether it does it appropriately or not. So jumping into the boring stuff, I have essentially two steps in deriving the optimal tax. The first step is to first you have to realize that Bob here mentioned externality. I mean, what the tax should be is equal to the damage that you incur by emitting an additional unit. That's a result that's super old due to pigou. It's called the pigou tax. So the first thing you have to realize is just that we have to figure out what the marginal damage is to people when we emit. And all the calculations will be about these damages and how to figure out how large they are. Step one, if you emit carbon dioxide into the atmosphere, temperature increases. Now that's a complicated process. We don't quite understand how it works. It works with a lag. It doesn't happen immediately, but it's fairly fast. Secondly, that increased temperature leads to economic damages. And I would say that actually the area where we know the least of all these areas is not the natural science area. It's actually the measurement of economic damages from increases in temperature. And I think we know the least partly because most of the people working on climate change have not been economists. They have worked on natural science issues because they're natural scientists. And I think we're realizing slowly that we need more economists to actually go out and measure the costs, the damages. All right, and they come in a variety of kinds. But now to put these things together, how do you think about them together? Well, the first thing I mentioned, how carbon dioxide causes the temperature to increase. Well, there is this relatively simple law that relates the carbon dioxide concentration in the atmosphere to temperature. And that's known to be a logarithmic relationship. So it's an increasing but a concave relationship. Concave means the more you add, the warmer it will be, but the effect will actually be smaller and smaller as you add more. So that sounds like a good thing because, yeah, it gets warmer if you add more and more, but actually the marginal increase will be decreasing. And that's a result that's due to actually Swedish economists. And this is a stamp. I'm a stamp collector, and I actually have this stamp in my collection. Svante Arrhenius. He came up with this rule like more than 100 years ago, and still today they mention it in the IPCC report. That's basically a central element of understanding what's going on when we emit carbon dioxide into the atmosphere. So that's one part. That's the first one. But then how does higher temperature cause damages? Well, many people have tried. Not enough people have worked on measurement, but the people who have, they believe to have a relationship that is convex, the opposite of concave. So it sort of looks like this. When you heat the globe more, damages go up, and they go up more and more in percent, or higher and higher percentage effects as temperature rises. So you have a concave relationship from CO2 to temperature, but then a convex relationship from temperature to damages. Put them together, it turns out that approximately the result is that add a unit of CO2, well, that's going to be pretty much a linear relationship in terms of percentage change in, say, global output. If you measure all the damages in terms of global output, you add a unit that's going to change global output by X%. And that X is independent of how much you've emitted. And that's actually, so putting together the concave and convex, that's actually the approximation that the numbers you'll see in a second satisfy. So if in particular you increase the atmospheric carbon concentration by 1 gigaton of carbon, that, according to available estimate, leads the world GDP to fall by 0.0024%. And where do I get this from? Well, there are many people who worked on these kinds of numbers. This is an average, taking an average over uncertain things, but Bill Nordhaus is maybe the most well-known one for having conducted meta studies where you essentially measure all kinds of damages that you can imagine, and then you try to value them in dollars and you add them together. And this number comes from that type of meta study. But there are other kinds of studies, they end up with roughly the same numbers on average. And this picture just illustrates that the mapping is linear, so actually roughly linear. So on the x-axis you see the atmospheric carbon concentration in gigatons, and we're actually, right now we're at 800. We're here. The blue line is Nordhaus's, it reflects Nordhaus's estimates of damages. They actually do depend on, so adding 1 unit, what's the yearly flow damage at current GDP? That's on the y-axis. Well, it's about $4 per ton. And the linearity is just saying that, well, that blue line doesn't seem to vary that much with how much you've emitted. So if we emit all the carbon that's left, or that the known amount of carbon, we end up pretty much at the right end of the figure. And you see that the marginal addition is still around 4. I mean, it's a little bit above in the middle and below right now, but so the approximation of a constant 4 is good, given available estimates. So that's for 1 gigaton of coal, and we've added 200 since the pre-industrial era. So the fact that we have burned fossil fuel has added 200. We might add 2,000 if we don't stop these 2,000 from being emitted. But what this means is that global GDP in a flow sense is down $400 billion US. Now you can decide whether that's large or small, but in percent, it reflects the number up there. So this is the flow cost this is the cost that hits world GDP every year by emitting 1 gigaton of carbon. And the second step in the calculation is that you actually have to add things up over time. So that's just the flow 1 year. Why do you have to add up over time? Because the emissions stay in the atmosphere for a very long time. So if I emit a unit now, it lowers GDP by some amount now, but it also does it next year and the year after that. So the carbon cycle describes exactly this effect. It turns out that roughly 20% of the emissions we make today stay for thousands of years, so long that you could think of them as basically staying forever. 50%, on the other hand, disappears immediately, or within a decade is gone into the biosphere, into the upper oceans. And then the rest, the 70%, the 30% that remains, slowly disappears, slowly goes into the oceans and disappears. So this is like a rough description of the carbon cycle that we've come up with that actually matches the data very well on how the carbon cycle works. So it tells you right away that, yeah, at least 20% stays for a very long time. So we have to add up all those costs in the future. But you can't just add up. You also have to weight them. Okay, so what's the weight we put on future generations? That's critical. It's called, to some extent, discounting, but it has 2 parts and 2 components. And one component has to do with the fact that future generations might be richer or poorer than we are. So I'm giving the example here. Suppose that future generations are richer. Well, in economics, you regard people as actually being less sensitive to income if they're richer. So if they're richer, they don't worry that much about risk, about getting it damaged by some amount. So actually, a common assumption that macro people make, and that is, I think, roughly appropriate, is to say that they care less, roughly in proportion to the level of GDP. But the conclusion from that then is that to calculate what the damage will be on a future generation, say 100 years from now, you don't actually have to know how rich they are, because if they're really rich, well, then the damages will be large. Because remember, the damages, they were constant as a percent of GDP. On the other hand, they care also in proportion inversely to GDP. So then we don't actually have to know how rich the future generations will be or how poor they will be. If they're really poor, they're severely hurt by damages. But on the other hand, the damages will be lower because they're poor. Damages are in proportion to GDP. The two cancel. So it turns out that that's a very robust result that makes the end formula very simple for actually what the optimal carbon tax is. So that's one part. The second part is that we may not care very much about future generations, or we may care a lot. That's what's usually called discounting. And I would say ultimately this is a philosophical issue, how much you care. In the well-known Stern review, the discount rate is 0.1, so you care about people 700 years from now about half as much as you care about yourself. Nordhaus, on the other hand, uses maybe 1.5%, a much bigger number, which means you discount, you care less about future generations. With that calculation, you care about half as much as you care about yourself of people who live just 50 years into the future. These are hugely different views on how much you care about future generations. So that's going to factor in. So when you sum everything up using these principles, you get basically a picture where on the x-axis you have how much you care, the discounting, and Stern is here, Nordhaus is here. I actually, on purpose, I put some Swedish here. And but you can guess this is discounting, right? And this is yearly. So it's Minnesota, so I thought you would all have an idea. On the left-hand side, you have US dollars per ton of carbon. On the right-hand side, you have Swedish kronor per ton of carbon dioxide. But there's a reason for this. So first of all, note that Nordhaus, in our calculation, for Nordhaus's discounting, you would have something like $60 US dollars per ton of carbon. And Stern would have almost 10 times. Of course, because they care very differently about future generations. But those are roughly the numbers. Now, are these numbers big? Even if you take Stern's number, 600 or 550, is that such a big number that the world economy would stop if you adopted those taxes? Well, I would argue not. Actually, Sweden, and that's also a reason why I put Swedish here, what you have on the right side y-axis are the Swedish numbers, and the Swedish tax is actually about 600 already. And Sweden seems to survive fine so far. And actually, it's kind of more difficult to have a tax if no one else has a tax. Because then you would think that industry moves, capital flows abroad. So actually, any type of calculation we have on this, even if you take Stern's discount rate as the kind of the right one, is we don't see any kind of big threat to our economies coming out of that. So this last figure summarizes, I think that if you want a number, here's the number, but it's got to be a function of how you care about future generations. And I'm not telling you how much or how little to care. I think it's up to us. So to conclude, I wanted to just add a couple of things. So the first thing is just to repeat that we must tax CO2 emissions, but the rate we need to tax it at is not staggering in the sense that it's not going to make the economy stop in any sense. The challenge to using a CO2 tax is that there's clearly global disagreement. There are, I think, strong lobbies against a carbon tax. So to that, I would like to first say, I think one thing to realize is conventional oil, like the Saudi oil, there's so little left of it in some historic sense that that's okay. There's not much conventional oil left. So actually, if you just burn up that oil, you can burn up that oil. The global temperature is not going to rise that much. So in a sense, typical gas pump prices, you could leave them alone. It's not going to change anything. What's going to change? There's like an echo here, right? Sorry about that. What's going to make a big difference is coal and non-conventional oil, because if you add up all the reserves of coal and non-conventional oil, that's such a massive amount that you'll be way over in the right end of that picture I showed you, and that amount, if you burn it all, is going to lead to a lot of warming and much larger damages than if you use huge damages compared to the optimal policy. Now, to conclude, I just want to say that in terms of discussing policy, it's very popular in many countries right now, I mean in this country, but in many other countries, to place your bets on green technology. I mean, it sounds like it's a great way out to figure out new technologies that make you less fossil fuel dependent. But what I would like to say is that if the green technology doesn't become so good that it basically competes out the coal and the non-conventional fuels from existence, if it doesn't make them unprofitable, there's sort of no point. I mean, so if first I say green in green, it looks good, and then I green in red. That's pretty impressive communication device. Because what I mean here, green in red, if it doesn't work like a tax on fossil fuel, it's essentially not solving the climate problem at all. But what worries me here is that everyone seems to be in favor of green technology subsidies and directing policy toward that. But when I say that, everybody, and I worry about everybody, because that means that the coal lobbies, the lobbies for these new fossil fuels, they seem to think it's fine that we're supporting green technology. I think that's the reason is they think it's not going to threaten them. It's not really effectively going to be a tax on them. And so we have to worry. I mean, if everyone is happy about green, that really worries me. I mean, really, in the sense of this analysis, if we have to do something. And yeah, so that's where I want to stop. I don't know how long that took. Okay.
Great. Well, thanks very much for inviting me, and I'm so glad to know that the University of Minnesota has invested in a very good sound system, apparently, out there. I want to pick up and in a way, focus on one specific issue. So you can view Per's comments as sort of the cake, and mine may be the icing. So I'm really going to focus on this notion of uncertainty and how that affects how we think about the economics and the policy relating to climate change. And my uncertainty, again, as Bob talked about at the beginning, it's not uncertainty about whether there are mechanisms leading to climate change and whether there is, whether they're warming or not. That's not the uncertainty, but really the uncertainty I'm focusing on is something that Per talked about, that what are the damages? If we have a certain amount of emissions, how is that related to climate change? And if we have climate change of certain severity, what are the damages associated with that? Okay. So first of all, several times it's been mentioned that in essence, most economists would view climate change and the issue of how to manage greenhouse gas emissions as a benefit-cost problem. So we could think about how much should we try to reduce emissions, talked about, usually referred to as mitigation in the climate change literature, and also not only mitigation, but how will we behaviorally respond? How are we going to adapt to climate change? And actually, there was a conference today, a workshop today at the Science Museum on adaptation to climate change. So one can think about, if we're reducing emissions, there's certainly, burning fossil fuel, or thinking about agriculture, which releases emissions, or land use changes. There are some benefits. There are reasons why people are doing these actions, but of course that leads to higher stocks of greenhouse gases and potentially more intense climate change in the future. So there are costs. Now, I'm not really going to argue against thinking about this fundamentally as a benefit-cost exercise, at least the economics of it. But I think there are some complications. Certainly one complication that many people have written about, and this isn't necessarily saying we shouldn't do this as a benefit-cost problem, but this is a problem that economists and scientists would call a global commons, right? So whatever emissions come up in Minnesota or whatever emissions come up in China, they mix in the global atmosphere, they basically have the same impact. Well, that also means that if we reduce emissions in Minnesota, or the good Swedes who have put a high tax on reduce emissions, but China or Brazil or India do not, most of the benefits that come from our actions are spread across the globe. Now, of course, the real problem here is that if you take the costs and most of the benefits go elsewhere, what incentive do you have to really undertake these? So you really need some type of proper global institution, and frankly, we don't have those as of now. So that's one issue, but I'm going to lay that off really to the side. I just want to mention that as an issue. A second important issue, and Per certainly mentioned this, is thinking about equity concerns or fairness. Who benefits and who pays the costs? So the second one down there, the intergenerational concerns. If we reduce emissions today, most of those benefits will be off 50 or 100 years off into the future because of the stock of greenhouse gases and the lag time that Per mentioned. But there are also certainly concerns even today, and thinking about intra-generational concerns. Who is it that bears the burden? Who would bear the, if we put an energy tax on, who would bear that? But if we don't put an energy tax on, if you're living in a poor island in the Pacific that only gets up 2 meters above sea level, you're probably much more concerned about this than, say, living in Minnesota. Okay, again, extremely important issue, and Per's graph that showed as a function of the discount rate how seriously or how high you would put the tax certainly shows the importance of equity concerns. I really want to focus, though, my comments on this last complication of uncertainty. There really are very large unknowns about how what we're doing now to perturb the climate system and Earth systems more generally will impact future generations. So I want to go through this just a little bit and thinking about this. So where does the uncertainty arise? Well, in part, the uncertainty arises because we don't really know what future trajectories of emissions are going to be, and hence what future stocks of greenhouse gases will be. This is going to depend in part on future policies as well as future technology. So if fracking is a good example. We have come up with ways to release economically much more fossil fuel than was possible even 10 or 20 years ago. So maybe we will pump much more carbon into the atmosphere by the time we're done with fossil fuels. And there's actually also here, the second point is there is a feedback loop. So the more that we emit today and the warmer it gets, there is possibly a positive feedback. So we might start melting permafrost, which releases more methane, which makes things warmer, which warms things up and releases more methane, and so on. So we don't really know what future emissions are going to be. Secondly, what about the climate system response? So the direct warming effects are fairly understood. There's sort of basic atmospheric physics here, but there are many potential feedback effects. So I just gave an example of the permafrost melting and methane release as one feedback effect. But there are other greenhouse gases besides carbon or besides methane. Water vapor and clouds are things that will affect the warming potential. As you get a warmer world, you tend to hold more water vapor. So, really the kind of climate sensitivity is a function of how much more water vapor and what form does that take, the clouds and so forth. So there are lots of potential unknowns about how the climate system responds. As much as we'd like, to keep it simple and talk about global climate, global warming, what's the average or mean temperature increase, what really matters for damages are what happens and where does it happen. So if you thought about a particular impact in the Midwest and in Minnesota, it's not so much temperature change that would matter, but what happens to precipitation patterns. So for example, in the summer, if we don't get regular rains like we get now, there's a big impact on agriculture. Agriculture, storm severity, sea level rise, all of these things are really where we're going to calculate where the big numbers are going to come from in terms of damage. And there's also uncertain cost of adaptation. Okay, so these various steps in going from emissions ultimately to future damages, there are many sources of uncertainty, but how should that affect how we or how economists approach the issue of what's the optimal tax that Per talked about. So is this just benefit cost with probabilities? That's certainly one way to do this, right? Think about the distribution, what's the likely outcome, take expectations, and think about how that would affect the optimal tax. Some have argued that we need to think about this differently, and I want to just walk you through some of the arguments on this. And I have to say, it was nice to hear, Per, you say you came into this with an open mind. It's not, you were coming from the outside. I also come largely from the outside. Most of my work is on interactions of economy and ecosystems, so I don't particularly have a stake in the climate change models, but I'll try to walk you through some of the people who have thought about this seriously and sort of where did they come out. So as Per mentioned, Bill Nordhaus is probably the dean of economists thinking about climate change. He's been at this for decades and has done some of the best work on integrated assessment models like what Per talked about. And certainly that would fit well in the sort of benefit cost approach. More recently, Nicholas Stern was asked by the UK government to put together a report on climate change, and he took a very different approach. I'd characterize it as an insurance approach. So under the insurance approach, you would think about, are there places that are too dangerous to be? So are there levels of climate or of greenhouse gas concentrations that are too high? He said roughly we should put a bound. Don't go beyond twice pre-industrial revolution levels, so around 550 parts per million. Don't go beyond that. And then figure out a cost-effective way of achieving that target. It's actually kind of interesting. So I worked at the Council of Economic Advisors back in the 1990s and thinking about both climate policy and also air pollution policy. Oftentimes, this would be the approach. The economists would not be charged with setting where clean air standards should be set, but figuring out cost-effective ways of meeting the targets once they were set. Okay. I wanted to press this point, is benefit cost analysis really the right approach? And Stern, in a paper in American Economic Review, I'll let you read it, but basically he says there is so much uncertainty in this problem, it's really hard to think about how one would optimally set taxes based on modeling of costs and benefits. Essentially, he's saying we need to take An insurance approach, there's just too much uncertainty. Now, I think that, and actually, let me skip over this quickly because I think Per did a nice job. If you think about sort of where do these different positions, the Nordhaus position, lead to in terms of an optimal price on carbon, you get different levels. It's harder to find actually where Stern says what price he would set, but it's clear that it's far higher than the price that Nordhaus would set. Now, there's a third economist who I want to bring into this mix, not just Nordhaus versus Stern, but Martin Weitzman from Harvard, who has written a lot also on climate change, and in particular about how uncertainty will affect how we think about climate change. I like this quote. He's going to come out on the side of Stern, but he said Stern got it right, but for the wrong reasons. Weitzman's really going to point to the uncertainty effect of pushing you to higher prices on carbon. Okay, so a very simple way to think about this. So the economists in the room, I probably don't even need to explain this if you're not an economist. The basic idea is or intuitive thing as follows. If we knew exactly where climate change would be, that would be like the dotted line, the temperature increase. But suppose that there's some risk. It could be much lower than that. It could be much higher than that. But on average, it would still be that dotted line. The question would be, what are the expected damages in it? If you've got these convex damages so that as you go to higher levels, the damages start to rise quickly. If you put any weight out there in the tail, out there further to the right, that's going to raise expected damages. And that's the essential point on any of this, the discussion that follows. Okay. In particular, Weitzman talks about something called fat tails. All you need to know about fat tails, this is not about Americans. What you really need to know about fat tails is that it's putting sufficient weight out on this sort of right-hand tail, this high expected change in damages, or high expected change in temperature. He came up with what he called the dismal theorem. I know that economists in general are known as the dismal science, and this is in particular then the dismal theorem from the dismal science. So how does he get to this? And effectively what he's doing is he's saying if you put sufficient weight out on very high temperature changes, and if those damages out there are sufficiently high, in fact they could be infinite losses, then you get this point that you basically have infinite expected losses associated with the risk of climate change. That's the essence of what's going on in the dismal theorem. And then you would spend all your money basically to avoid this infinite loss. Okay, now there's three important components of the dismal theorem. It's that you put sufficient weight out there, that there are huge losses if temperatures go up by very much, and that basically, sort of unbounded losses. So if consumption goes to zero, you're going to say, oh, that's a catastrophe, and basically infinite losses. Okay, so large consequence and sufficient probability on that large negative consequent event. All right. If you really take Weitzman's argument seriously, it shows the difficulty of applying benefit cost to climate change, because you're basically saying, well, if you perturb the probabilities out there of these really bad events, maybe you spend everything. And I'll show you in a moment that maybe you don't spend everything. But there are non-economists who have been kind of seized on this and said, this is a pretty strong statement, but basically saying we can't believe the benefit cost approach that is taken by economists for these kinds of reasons, because there's this potential for catastrophe out there. Okay, now I have my own critique of Weitzman's model, which I think of as sort of tricks with infinity. I don't know if you know Letterman's sort of stupid pet tricks, but anyway, tricks with infinity. But there's two ways easily to get out of this, tricks with infinity. One is something that Bill Nordhaus himself and Robert Pindyck have said, that marginal utility is not really infinite. I mean, you don't have these infinite losses, and that's certainly one way out. And you really do need infinite losses to get Weitzman's result. The other one is a paper that I wrote with Chris Costello and Andy Solo and Mike Newbert, basically just put an arbitrarily high but finite limit on how high you think temperatures can go. We certainly aren't going to get as warm as the sun, and well short of that. Okay, so the question that Weitzman asked and that we asked is, what fraction of consumption of GDP should you be willing to spend in order to avoid uncertain losses from climate change? So if you could buy perfect insurance, how valuable would that perfect insurance be? We took a temperature distribution that has a fat tail, so you can't really see it, but it keeps going on out beyond 50 degrees C increase, which is far, far higher than any climate scientist which would think is reasonable. We have the same kind of approach, the utility function as Weitzman. We allow the economy to grow like Weitzman in the absence of temperature change, and we parameterize it for saying maybe it's a 3% loss of consumption with 4 degrees C warming, higher losses as you go up. You can play around, and we did with these parameterizations. Okay, so Weitzman's result, the Dismal theorem, with no upper bound in temperature, infinite losses, you'd pay all of your income to avoid uncertain losses. You just put a bound, and I'll show you in a moment. Any finite bound, you get out of the Dismal theorem. Okay, so for example, if you put bounds of, say, 20 degrees C or 30 degrees C or 50 degrees C, which is far, far higher than anybody's talking about, you change the Dismal theorem of spending everything down to ranges that were similar to, a little bit higher, but similar to what Per was showing. You know, maybe this is on the order of less than 1% of GDP, or maybe it's 2%. So in summary, it's not that the Dismal theorem is relevant for policy, but I do give Weitzman a lot of credit for the following. What is important, and I think very troubling, is the influence of these low probability but high consequent events. And these are things we can't rule out now because of the uncertainty in climate change, or uncertainty of our science and understanding of what future damages are going to be like. Even small changes in the likelihood of these very high consequent events give us a large change in expected damages. Okay? Now, these are precisely the kinds of events that are very difficult to predict ahead of time, right? So they're not likely to happen. We're into a system which is going to behave very differently in the future, potentially, than what it does now. So it's hard now to know exactly how likely these events are. Okay, so inclusion of uncertainty will almost surely raise the carbon tax, but exactly how much it raises the carbon tax depends upon sort of how much probability you put out there, how severe and how likely are those kind of big scale or catastrophic climate change events. I don't have an answer for that, and I think, you know, the troubling thing is I'm not sure how I would have an answer for that now. And if you combine that with kind of the political climate that we find ourselves in these days, where it's difficult even on things that the science is pretty well understood and not very controversial within the science world, out in the larger political world we have a lot of strongly entrenched positions, and things are very difficult. So now if we're trying to communicate saying, well, you know, maybe the tax should be higher because of a small change in the probability of some unlikely future event, I think that's a very, very difficult thing to communicate effectively. Okay, so where would I end up, though? That's kind of a negative message. I think what it tells both the natural science community and the economics community is we ought to be thinking about robust policies. Robust policies are ones that generate acceptable outcomes under a wide range of circumstances. That maybe we ought to be especially careful about places where, if there are thresholds in the natural science response. So is there evidence from climate science of dangerous levels or places where we would get really steep increases in marginal damages? And then the third thing I would mention is that we ought to be able, you know, we are going to learn things through time. So we're going to accumulate evidence, and we're going to want to adjust future policy given that new evidence. But one thing then that is a well-known principle both in finance and in economics is this notion of option value. So if you don't know exactly how things are going to play out, you want to maintain flexibility until you learn. And so we want to avoid things that bind us in, perhaps too high levels of carbon emissions, stocks, unless we have a way of backing out of them quickly. So I'll just give one final thought, which is, again, I'd sort of set this out as Nordhaus versus Stern, or cost-benefit versus an insurance approach. And this is a quote, and it's particularly from a recent book called Climate Casino. And if I don't tell you who this is, you might guess this is Stern, but in fact, this is Bill Nordhaus's most recent book called The Climate Casino. And with that, I'll say thank you very much for your attention, and we'll now turn it over to the panel. So.
Well, we've got, I guess, about half an hour left, so a little bit less time than we had budgeted. I think I am perhaps given a few minutes here to react to the two previous presentations and ask a few questions, and then we'll turn it over to the audience. First of all, I thought those were excellent presentations. I didn't find anything that I particularly disagreed with. Let's start with Per. Per suggested that it would not be, the appropriate price would not be a price that would cause too much harm. Certainly that's been my thought all along. The sad thing about climate risk is that it would be so easy, actually. I think an appropriate tax, which I would guess would be somewhere in between Nordhaus and Stern. If you asked me, I have no particular number, but I think probably $20 per ton of CO2. I think you were talking about carbon, so that's a factor of what, 3.6 or something? So if you want to know the C number, multiply my number by 3.6, but I think most people talk about CO2. So $20 per ton of CO2 would be a tiny impact, and yet I'm pretty optimistic that over time would cause emissions to go down, but you don't know. I think that's at the lower end, and maybe at the upper end might be $100 per ton of CO2, at which point a lot of technologies to reduce emissions become very effective, and over maybe 10 years, the amount of emissions would go down very, very dramatically. I think it's pretty well. We know a lot about the demand curve for emissions production. Which isn't to say we wouldn't learn a lot more. And another reaction I have is to Steve's point right here at the end. There's a lot to learn. And when we build models, I think it's very important to recognize that there's going to be a lot of learning, that we will know a lot more in 10 years or 20 years. Maybe not about the ultimate damages, the economic damages, but we certainly, if we were to price emissions, would know a lot about technology and the rate of development. So for example, if you ask me the question, what's the upper bound on emissions, there are technologies today for sucking carbon dioxide out of the atmosphere. You can grow trees and bury them or something along those lines. I think the current estimate is something like $600 per ton of CO2, and that probably would come down dramatically if society put its mind to figuring out what's the cheapest way to suck carbon dioxide out of the atmosphere. Of course, it's a lot cheaper today if you try and suck it out of the high temperature emissions from coal-fired power plants. So carbon capture and sequestration is much cheaper than that $600 a ton, but we could do that, and as many scientists think, we may have to do that at some point. Well, then that gives you kind of the current price is the expected discounted value of the future price of sucking carbon dioxide out, because we're going to put it in the atmosphere today and then we're going to suck it out. You don't want to charge people more today than it would cost to suck it out in the future, maybe taking into account damages in between. So I think there are some margins like that we have to think about, and in building these models, I think we have to think seriously about call it a robust optimal control. We have a problem here that we're going to try and deal with, and we're going to deal with it over time as we learn more. There may be nonlinearities, there's a lot of uncertainty, and so it's a complicated problem. And if I could just give one analogy, and this gets to not only what's the appropriate price today, but what's the appropriate time path for emissions reduction, for pricing emissions reduction. And it seems to me, if you think about two scenarios. The first scenario, I like to ride a bicycle in the mountains. So think about riding down a mountain road. If you've been in the Pyrenees, that's a good example. You've got mountains on this side, you've got a cliff on this side. It's beautiful, but you're going down this road. You see a curve up ahead. In scenario one, you've been down this road many, many times. You know that you've got to slow down as you get into that curve to go around it safely. You might know that with good conditions, you can get around that corner at 15 miles an hour. You're currently racing at 25 miles an hour. You know when and where you have to start applying the brake, and the brake being the price of emissions. And you know that you're going to start applying it at a low level and increase it over time as you get into that curve, because there's not a lot of uncertainty. You've been down this road and you know how it works. In the second scenario, which I think is more realistic, we've never been down this road before. You don't know how tight that curve is. Maybe it's a rainy day, a little bit of fog, and you see that curve up ahead. You're going fast. You realize the road is getting a little more steep. You realize that that's a very steep cliff. If you lose control, it could be very bad. And you get sort of this, as time compresses, you realize, I might be going too fast. I might be out of control. There's a small chance of a catastrophe. And so what you do at that point is you grab the brakes hard. You say, let me slow myself down until I feel I'm more in control. And so the time path of that braking is very different when you take uncertainty into account and when you take risk aversion into account. And you might actually want to grab those brakes so hard that you expect to ease up on the brakes as you expect to get under control. And this is a statement about discounting. Basically, if you're very risk averse and if you see a high enough probability of catastrophic damages, which doesn't mean it's high, but high enough, then you might react very differently, and you might want a very high price as we gather more information and move down this road. So that's my reaction, and maybe I'll open it up with a question for Per and ask, when you say that you think the tax is relatively low, do you mean by that people wouldn't notice, or that and would it have the appropriate effect of reducing that small chance of catastrophe?
Well, so I'm starting from the end. This is our calculation, and I think our calculation takes into account uncertainty. It takes into account, of course, like with any calculation, we might be using the wrong numbers, and you could always say with any calculation that we're not cautious enough, but we're trying to be cautious, and we came up with a number, and I think that's a good number. And the tax that we're talking about is, again, it depends on whether you use the Stern discounting or. But even the Stern discounting, surely people will notice the gas price going up if we're applying the tax to gas. I think it's like $1.50 per gallon. So that's a big amount for the Stern type of tax.
Yep.
If it's a Nordhaus type of tax, it's 15 cents. But the world wouldn't stop. And if you look at European gas prices, they're kind of much higher than here. And so, yeah, I think, what I do think we have to do is we do have to roll up our sleeves, do some serious calculations, take all of these things into account, take into account severe risk aversion if you'd like. And I have to say we didn't use an extreme amount of risk aversion in our calculations. The numbers would go up if we used more risk aversion. But do that, be explicit about what you do, calculate, come up with a number, and I think that's it. And if we keep doing that, I think we'll eventually end up in the right place.
Okay. And Steve, you mentioned that this Weitzman dismal theorem and your reaction to it, which is not to use the infinite utility. But does that leave you then more optimistic about how this is going to work out, or where do you come out on that?
Yeah, no, I mean, if you take a sort of a base case, a Nordhaus or Per's numbers of, where were you, 1% or around that, there's a big gap between 1% and 100%. I think the point is that putting in uncertainty, which I do think is quite important, but putting it in a reasonable way leaves you more on the order of 1 to 2 to 3% rather than 50 or 80%. And I actually think that that's a hopeful message because, I hope Per is right in that this isn't that tough of a problem, because I think if you are going to put, basically the policy decision here is something of a negative message, right? We need to tax carbon. We need to tax fossil fuels. We want to raise prices on certain things. So the less bitter medicine you have to put out at the time, I think actually that part, I would say, is hopeful. So the direction is, I think, increasing uncertainty or taking that into account in a serious way pushes up your numbers, but I don't think it pushes you up. I don't think it would actually take you outside of that range that you initially said about price between $20 and $100 per ton of CO2.
Okay. Let me offer either of you the opportunity to respond to the other. Were there any things that either of you heard that you'd like to question or push back on?
You've had more time to think because I presented first.
No, I mean, I've had the advantage also of seeing the slides ahead of when you did. So, no, I thought you did a very nice job of laying out the basics of climate change and the integrated assessment models and how we would go about it. So, we might differ, I think, really at the edges. What would we take on uncertainty? And I guess this comes from my work in thinking about integration of ecological systems and economic systems and sort of how little we know about responses like what will ecological systems look like in 100 years under a very different climate, how fast would they migrate, and what does that mean? In terms of, though, how much that matters for the economy in terms of economic growth or responses there, I think it's unlikely to be catastrophic. So anyway, I appreciated your comments and laying out the basic approach so clearly.
Okay, and I mean, so I agree with most of what you said. I mean, the one clarification I would like to make, maybe more relative to my presentation, but it relates to your presentation, is this cost-benefit analysis or the tax approach versus what you called maybe Stern's approach or the insurance approach, which is that you decide, well, we don't want to exceed a certain level of carbon concentration in the atmosphere. And then we figure out how to get there, but we put an upper bound and that's it. Like, when is such a policy good? And I would say it's good if we really, either if we're just extremely risk averse, we don't know anything, and I don't know why we would come up with what number we would come up with, but so that's kind of an open question. But another reason we might like that is that if we know that there is a global tipping point at 1400, I mean, we're at 800 now, if we knew that there was a global tipping point at 1400, I mean, that there's a reason to really focus more on the quantity and making sure you don't exceed 1400, let's say 1300 to be sure, right? But that's not that's not the correct summary, I think, of what natural scientists tell us today. I mean, I'm not an expert. There are lots of small tipping points. When I say small, I mean they could be huge for the local community, but there's local tipping points all over. But in terms of adding all of these up and adding up the damages like I do when I'm a cost-benefit person, it still adds up to something that is not hugely nonlinear at any particular number. So that's as far as I know, what we know today. But we may find out that actually there is a global tipping point at 1400 or some other number. Of course, then we have to change. But I don't exactly see that. So until then, I'm sort of happy with the optimal tax, typical, standard, boring, cost-benefit, taking into account uncertainty and risk aversion.
But, and let me just conclude here by saying, I take it both of you would not be comfortable saying, let's wait and see, that you would agree that we ought to be imposing some incentive here to conserve emissions immediately.
Yes.
Yes. We may not know exactly what the answer is, but I know the answer isn't zero.
Yeah. Okay, I think we have about 15 minutes left, or maybe even slightly less, so let's open it up for questions from the floor. I think there's some microphones on both sides, so just raise your hand and we'll take some questions.
Hi there. I'm actually a student of economics here at the university, and yeah, it is one of the better programs that I've seen around. I completely agree with you. But
What do you have to compare to?
you could say I'm a little biased. But I guess my question was more, being that there's the typical undergrad life, you deal with a lot of people that are much of the Ayn Rand persuasion. I guess I'm curious how you would respond to people that would say that there isn't a duty of a government to respond to climate change and that the free market will resolve it. I guess what would you, either or any of you, respond to that kind of claim with?
Well, I mean, that's just the idea that the market cannot deal with these pure externalities. I don't see how that would happen. I mean, if you somehow assign property rights to the atmosphere or the weather, but it's not going to happen, and it's the purest externality there is. Like you just said, that you emit something here, it will be in China within a year. I mean, it will spread kind of evenly. So then you need an additional mechanism. You need a tax or something equivalent to a tax. I think everyone agrees with that. I think the skeptics, they say more like, I don't believe there's warming, or it will lead to economic disaster. One of those two things is, I think, the most common reasons why people don't like this.
There is this is kind of outside of economics, but where did the skepticism about climate science, which most people are not climate scientists, but now we've got lots of experts on climate science. Where did that arise? And there's a book out there. Naomi Oreskes is one of the authors, but it's basically saying that the reason that you get antipathy to climate solutions because it is an externality and because it then seems to require government action. So if you have people who are very much in the Rand school of thinking, you don't want to go that route. So let's deny the problem in the first place, which is exactly the wrong solution. I mean, if what you don't like is government intervention, well, let's figure out ways of perfecting property rights or coming up with market-like solutions, cap and trade, for example, in this realm, rather than going back and denying the problem in the first place.
Indeed. There's a question back here.
I'm wondering what the Swedish carbon tax money that's taken in is used for. And then, like you said, Sweden is taxing carbon. No one else, well, there may be somebody who is. And however, the problem is being produced all over. You just mentioned, of course, carbon dioxide and so on travels through the atmosphere, and so on. But what is Sweden using the carbon tax for?
We got an email in my research group from a non-profit organization where someone had calculated that if we would just use the appropriate level of taxes in Europe, it would solve all the debt problems because of all this revenue we would get. And it looked too good to be true, and it was too good to be true because they had missed 1 or 2 zeros in the. The fact is that the revenues are not that big, so it goes into the general budget and disappears. I mean, it's a small amount, really. So partly has to do with the fact that the tax isn't that big, but there's just not that much fossil fuel. So it's not really that budget relevant in Sweden or in any other country, I would say. It's just marginally going to improve budgets.
If I could just add to that, there was an interesting debate in the U.S. About a year ago when the EU tried to put on a tax on aviation, and there is a Senator Thune who basically proposed a law prohibiting U.S. airlines from paying the tax to Europe, and it was interesting for a number of reasons. There was bipartisan agreement. I think one of the only bills where there was bipartisan support to oppose allowing U.S. airlines to pay this EU tax, which actually has not gone into effect. But what I thought was very interesting in the debate was every senator from both sides of the aisle said that one of the fundamental problems with this tax was that the EU could not guarantee that every cent of tax would be used to mitigate emissions. Totally missing the point that the reason for a tax is to incentivize conservation of emissions itself, not to pay for emissions. If you create the right incentives, you don't have to worry about, in fact, you can give that money back to the people or use it for other purposes. But that was the reason they all cited why we couldn't go along with this tax, because it couldn't be guaranteed that every cent would be used for emissions reduction. All right, another question up here.
You talked about the relationship between.
Let's.
I think you talked about the relationship between CO2 emissions and then temperature to GDP. I'm interested in another relationship, possibly that relationship to CO2 to GDP. In other words, as the GDP grows, do we tend, in the world that we live in today, growing at, let's say, 4% or 4.5% a year globally with 7 billion people, with the kind of standard of living that exists today and which changed slowly, an increase in GDP of, say, 1%, would that, what would that do to the emissions of CO2?
Here,
Yeah.
Steve?
There have been people who have looked at both emissions cross-country and then across time. And basically, the general point is that as you get richer, the per capita emissions tend to rise. But they rise, as you get richer and richer, they rise at a slower and slower rate. So you get this kind of concave relationship. There are other pollutants where economists have found a different pattern, the environmental Kuznets curve. So air pollution in a city where initially you get, if you go from very low levels of income to moderate levels of income, you get a lot more gas-burning vehicles. They tend to spew out a lot of emissions. So, the worst places in the world for air pollution are places like Beijing and Bangkok and New Delhi. They're not New York and London. So, you tend to get more spent on environmental improvements. You go up. But there hasn't been that kind of pattern shown for CO2. And I think largely because it is a global pollutant. It doesn't have the kind of, people aren't going to put up with Beijing-style air in a rich country, but not so for carbon.
This question over here.
Have the integrated assessment models been checked from historical data?
I don't think the mic is working so well.
Okay. Have these integrated assessment models been checked from historical data? Say we have so far had so much increase in CO2. Is the data available to say, oh, we've had this much damage?
Some, but not that much. I think the real problem is in the damage measurements. I mean, there's a type of damage assessment study which essentially just looks at weather changes, like temperature increases and temperature falls in a cross-section of countries for as long as we have data, which is not very long. And then they come up with numbers that are actually quite similar to the numbers that I reported in a flow way. Of course, that's very reduced form. You just see the temperature goes up, GDP goes down. Temperature goes up, mortality goes up, etc. So there are those studies, but I think the main problem is the kind of Nordhaus meta-analysis where you measure on the micro level all the costs of the different kinds. We haven't done that for more than 10, 20 years. So historically, it's very hard to measure damages other than with this reduced form approach, and that those results they're not super solid, but they're consistent with the numbers that I showed.
Are those studies then the benchmarks for the integrated assessment models?
So I didn't hear.
Are they the standard of comparisons for the integrated assessment models?
Are there standards of comparisons?
Yeah, the studies that just look at temperature going up and income, then effect on income.
Are those standards?
Yeah.
Those studies.
Yeah, I would say.
Okay, a couple of questions here in the middle. And then I think we're going to have to wrap it up.
Right, hi, thank you. So I think it's been made incredibly clear that climate change is an issue and that a solution needs to happen. But on a national level where people still deny that climate science itself, how do you convince those people that this needs to happen? And on an international level, the point was made that there's no there's effective global body to regulate this. How do we create a policy or some sort of initiative that can design this solution? Because as of now, in the motorcycle example, people aren't even aware that we're heading towards the curve. How do you generate that awareness?
I think there is increasing awareness. I think, as Bob said, that you hear less and less critics. I mean, I think as time goes, I think it's a matter of education actually. That you just more and more people are studying the issue. I think the people that deny, I think the basic mechanisms that are out there, there's just fewer and fewer of them, and I think it's correct that there are feedback mechanisms, and that some feedback mechanisms can actually make the problem less severe. That's true, but my sense is that, of course, some people you can never convince, but I think like the fraction of people who believe this is an issue is rising, and maybe it's not going to go to 100%, but it's I think it's on its way. So I'm mildly optimistic. I don't know what you guys think actually.
I lived for a year in Sweden, and when I was in Sweden, I was more optimistic than when I live in the U.S., where, so there's a handful of countries, the U.S., Australia maybe, where this issue has gotten ensnarled in partisan politics. It's definitely not that way in Sweden and much of the rest of the world. And unfortunately, when it gets involved in partisan politics, it's sort of one side and the other, and people then selectively use data, and it's frankly, I think it's hard to get out. I hope you're right that we can, and certainly at a state and local level, you see much more agreement and actual actions. State of California, many cities. In Washington right now, climate, along with almost every other policy one would want to talk about, is ensnarled in gridlock, and I don't see an easy out.
Yeah, I guess I'm more of an optimist, although it's easy to get pessimistic sometimes when you listen to what the politicians are saying. But I think fundamentally the problem is a global problem, and we don't have a good global governance structure to address this. But there are some promising signs. The aviation industry, for example, has just about a month ago agreed to create a global market-based measure for pricing emissions in aviation. And now, they said it will take 3 years to do it, and then it won't be implemented until 2020. So you can worry about the delays, and you can be a cynic about, are they really going to do it, and at what level, and so on. But if we were to get an agreement to price emissions in aviation, I think there's other sectors like maritime transportation that would be very happy to adopt such a global pricing. And if that were to happen, I think I'm convinced we're near a tipping point where people would actually say, you know what, this is a very serious problem. It's time to do something about it. So
political tipping point. Right?
yeah, it's a political tipping point, indeed. So who knows? I could easily be very wrong, but I'm relatively optimistic. All right, there was one more question here in the second row. Yeah.
Well, it's a bit of a technical question. That was a very good question, I thought, for ending it. But Steve, I appreciated your comments on Marty Weitzman's modeling, and I've read it. I appreciate your discussion of the Marty Weitzman's modeling. I've read those papers and thought about them a lot. And I guess I would say that he was less fixated on the infinite problem than he was on saying to Nordhaus and others that this suggests that we really got to get going faster, sooner, that this kind of moderate sort of ease into it is just not going to work given the huge possible risks involved. And the other thing that I don't think you mentioned that I think was really important in the Weitzman piece was that the uncertainty throughout the various factors that lead to the damages from the CO2, the actual scenarios for the emissions and their effects and whatever, that gets propagated through those PDFs all the way to the damaged PDF. And I would just say one more comment based on that, and that is that I'm not so optimistic about uncertainty being reduced in the future. And there's scenarios in my mind where it could increase. There are such things as unknown unknowns, and there are some factors we really don't know enough about, aerosol effects in particular, which could have a very, very big impact when we start reducing the man-made, the human-made aerosols. There's just some recent, speculation on that, but those are just examples where uncertainty could loom larger in the near future. Hopefully, it would dampen down.
Yeah, no, actually, Weitzman has written various places where he, in some sense, the dismal theorem sort of took over. And I completely agree with you that really his point, and I actually tried to make that, is that the point is not infinite losses or that we'd spend all that, but including uncertainty increases the severity of the problem and would raise the optimal tax, if you will. Now, again, the question is sort of how much, and that I think that's a difficult question to answer because it depends upon how likely you think some of these various serious tipping points or very serious consequences are. And I don't see an easy way to answer that for exactly the same reason that you're saying, is we don't really know how this complex system will react in a very different state than it is now. So I don't think I would disagree with any of your comments.
Okay, well, why don't we thank the panelists?
So that was great. Thank you, Bob, Per, and Steve, for a phenomenal discussion. I think it gave. I understand the economic issues a lot better. And I've thought a lot about this after this presentation. I hope all of you did. So I do want to thank the three of them. I also want to thank the interim dean of the College of Liberal Arts, Bud Duval, and Regent David McMillan. The Institute on the Environment is also located at the University of Minnesota, is doing great work on this stuff. Copies of their publication, ENSIA, are available on your way out. Perhaps the most important thing I have to say is that the Heller-Hurwicz Economics Institute has started putting out regular policy briefs on important issues. Our second policy brief is actually authored by Bob. It's on time and time compression. Copies of it are available on the tables. Please feel free to take one of them, or if they run out of copies, please feel free to go out on our website, Heller-Hurwicz Economics Institute, and you'll find it there as well. So what I'm going to do now is to give tiny tokens of our appreciation to Steve there and
They're all the same?
For you, what we tried to do was